Hello, Daniel, Cole, Neil, and I will talk about what makes a weed whacker whack. To start off, a weed whacker is a device that cuts plants with a rapidly spinning string.
So a weed whacker has a two-stroke piston engine where gas is injected into it through a carburetor, using a primer bulb and a string pulley to get it going. Then the buildup of the fuel-air mixture in the combustion chamber of the engine allows a spark plug to ignite, combusting the mixture and generating enough energy and angular momentum to keep the rotor spinning. So what's a carburetor? In short, a carburetor is a device used in many combustion engines that controls the amount of fuel that gets mixed with air to be used for combustion. It is the main engine component that allows the weed whacker to function. So a general outline of the carburetor system can be defined by this flow chart. Gas from the tank goes to the carburetor, while air enters the carburetor through a choke valve and mixes with gas in the venturi. The mixture then goes through a throttle valve, where it exits the carburetor and is checked by a reed valve. After this, the mixture can combust due to ignition of the spark plug in the combustion chamber.
Now we'll explain the nitty-gritty details of the carburetor. A sucking effect is created at the throat by decreasing the pressure at that region. This is because the flow can be assumed to be inviscid, steady, and incompressible up until the throat, and we can trace a streamline which starts from the static atmosphere, goes through an air filter in the choke valve, finally arriving on the throat, meaning the Bernoulli equation can apply. Static pressure along the streamline must be exchanged with dynamic pressure to maintain the total pressure. A decrease in the cross-sectional area at the throat of the venturi increases the velocity of the flow, which increases the dynamic pressure, causing the static pressure to decrease. The starting process of the weed whacker takes the choke valve from full choke to half choke to off choke with additional steps.
So for our numerical analysis, we're actually going backwards in the starting process because the steady state is simpler to analysis. The major twist for the real carburetor is that the pressure difference between the throat pressure and the fuel tank pressure must be able to combat the pressure loss in fuel lines. Using the assumptions as mentioned before, we calculate the pressure drop by first getting the volumetric flow rate with volume change caused by piston motion, which is the amount of fuel-air mixture that needs to go through the carburetor for each cycle, a fuel-air mixture ratio, and the engine revolutions per minute. The volumetric flow rate of air then gives us the speed at the throat, and using Bernoulli, you can get the static pressure inside the throat. To calculate pressure loss, we use the volumetric flow rate and the density ratio of liquid and gas fuel to get the speed of the fuel inside the pipe, which allow us to calculate the Reynolds number and sequentially friction factor and pressure loss. So here are the results. The Mach number of throat we get is close to the compressible limit, but we believe it's still reasonable to assume that the fluid is incompressible. One noticeable fact is the Reynolds number inside the throat, which is around 43,000, is much higher than the transition Reynolds number from laminar to turbulent. And this causes turbulence in the flow and makes the fuel and air better. Calculate the pressure difference between the throat and the atmospheric, which is what we assumed when the fuel tank is almost empty, is 7.87 kilopascals. And the pressure loss calculated is 3.27 kilopascals, which is lower than the pressure drop. So this allows the engine to function properly. But when the engine is just starting itself, the choke valve is at half choke location, which we'll explain later. The major difference here is the engine runs at a lower speed, and our calculation shows that the pressure drop will still be greater than the pressure loss, even with engine RPM as low as 2100. And this allows engine to automatically reach steady state once it's started. However, when we go a step forward and the engine is cold and it's not started at all, we have to choke the engine completely by closing the choke valve and leaving only a tiny hole on it. The reason why we choke it is because when the engine is cold, fuel will not vaporize correctly with the steady state fuel to air ratio, so a richer mixer is required. By closing the choke valve, very little air can go through, so the rest of the volume must be pulled from the fuel tank. But to kickstart the engine at the very beginning of a primer bulb is used. It pulls fuel from the tank and pushes it into the carburetor while being released and pressed. So this is the MATLAB theory we use to calculate pressure.
Finally, here are the sources that we use for this project. Thanks for watching and for a great semester.